All right, so welcome to the first lecture for Stat 478, which is Applied Generalized Linear Models. Fun fact, this is the very first time this course is being taught as Stat 478. I actually taught this course once 2 years ago when it was still listed as a Stat 495, but the course was pretty much run. The course is run pretty much the same way with some differences in assessment. Anyways, this course is an extension of Stat 378, which is the Applied Regression Analysis course that we teach at MacEwan. So in order to get into this course, of course, in order to get into this course, the assumption is that you would have gotten at least a C- in Stat 378. And oh, wait, sorry, one sec. I should have the. That's weird. Okay, clearly copy and pasted over that. Anyways, the assumption is that you would have taken Stat 378 and Stat 265, I believe. It's either Stat 265 or 266, but I think it's 265, and I'm just going to confirm really quick. Either way, if you're registered in the class, it's because you have the prereqs, but the point of bringing that up is just to effectively remind you that there will be concepts that come out of those courses that you will have, the assumption is that you have seen before. But those should be in the course outline. So I will add that because that is a mistake on my part. 266. So it's Stat 266 and Stat 378, and that should be listed here. Okay. So today, what we're going to do is basically go over the course outline, so the details of the class. We're going to talk about the assessments in the class, so assignments, projects, tests, and final exam, the weighting associated with those. We'll look at a tentative course outline, so the schedule of topics, and then we'll start the first lecture set, which is basically just review of Stat 378. And we will talk about the first assignment and about the project so that everyone's on the same page in terms of expectations and what they have to do over the next couple of weeks. The project isn't due until the last day of class, but the first assignment is due in the next couple of weeks. All right, so I have taught all of you before. Boyce and Kevin and Romessa, I had you last semester in Stat 324. Kevin, I've taught you and Jordan last year in Stat 350. Pretty sure you were in that class, Jordan. The way that this course is going to run is very similar to Stat 350. So this is a more traditional statistics course, in that I'm going to use more of my sort of like lecture slide based approach, and we're going to look at examples and concepts through that type of display rather than the kind of written lecture note style display that I used in Stat 324. It's also more traditional compared to the other MacEwan courses in that, like, we're not doing coding from scratch like we were in Stat 324. There will be an R portion of the course. I'll talk about that momentarily, but it'll be more or less run using like built-in functions and things like this. If we do any kind of cross-validation, we might use maybe use a for loop or something to do that. But for the most part, it's just going to be using kind of like the functions that exist in our like GLM will be a big one because that's the generalized linear model function. Okay, so office hours, I'm going to have 2 office hours a week. Those are going to be on Wednesday and Friday from 10 to 11. The office hour will be online, at least for the first few weeks. And the link for the office hours is given in the course outline, and it's also given in the course content folder of the webpage. If you need to meet with me outside of the office hour, that's perfectly fine. Just send me an email and let me know when you'd like to meet, or even what the question is, and maybe we can just handle it through email. Either way, I'm flexible with my schedule, and we can always work out a time to go over course material. This class, as I had mentioned before, has a lecture and a lab component. So the lectures are Tuesday, Thursday from 11 till 12:20, and the lab is Wednesday from 12 to 1:50. So it's actually a pretty heavy course in terms of the amount of hours spent on this course per week. So there's roughly 3 hours or 2 hours and 40 minutes of lecture. And then there's an hour and a 50-minute lab, so about 2 hours. So that's almost 6 hours of coursework a week. It's very unlikely that the labs are going to run for the full 2 hours. There's just realistically, like, there's not enough material to go through each week in lab in terms of learning how to fit these models in R that we would need to spend that length of time. So some of the labs might not be 2 hours in length, but the rest of the time can be used to work on the assignments and to ask questions. So that sort of a built-in working session, which I think is valuable in these types of courses. So I encourage you to take advantage of that and not just look at it as a free hour where you can go and do something else. Okay. This course was and is scheduled to be an in-person class. So right now, as you're probably aware, sorry, just reading this. Anyways, I'm gonna fix that up after. But this course was scheduled to be an in-person course. So right now it's completely online until January 21st, based off of the current COVID situation and how the university wants to handle said situation moving forward. The expectation is that we will be in person after January 21st, but obviously this is an ever-changing situation, and whether or not that actually comes true, we won't know until we get closer to that date. The last email that I had from the dean basically said, like, there isn't really any update at this point, just treat the classes as online and we're going to move forward. So with this class, we're in a good situation because there's only 4 students. So any room on campus is going to allow for us to socially distance appropriately and accommodate the size of the class. So I'm confident that we're going to be in person at some point this semester, but I can't say for sure when that's going to happen. But with that being said, I'll keep you posted on any changes. Until the 21st of January, we can just assume this is going to be an online class. And then we're just going to take it, week by week after that and just see what happens. So this blurb here about the every 2 week thing, that would be in the situation that we turn to a hybrid class. And again, I don't know if that's going to happen. So like I said, I think the best thing to do right now is just treat it as an online, and then any changes that are going to come, I'll let you know, and we'll just move forward from there. But I mean, it is important to keep in mind that in the event that we're able to move back to the in-person / face-to-face style, we will do so. And the expectation is that you will be there for class. Okay. All right. So with that being said, we're going to basically survey a lot of the different topics that occur within the generalized linear model suite throughout this semester. And we're also going to talk a bit about survival analysis. I'll show you some more detail on this on the schedule momentarily, but this class will be in the beginning fairly theoretical, but we will have the lab component to try and to ground the theoretical aspects of the lecture and give some practical examples of how these models can be implemented and how we can interpret and work with the models, which at the end of the day is the most important aspect of what we're trying to accomplish here. So we're trying to, really build up your toolbox of statistical tools and help you recognize situations where you can use these extensions of the linear model for data sets where the response variable is not normally distributed. But in order to fully have a good understanding of the situations in which you would apply these, we do need to study the theory and the development of the models as well. And that's really what we're going to work on over the next 3 or 4 weeks or so before we start to get into the applied situations and the different types of models that are available to us. So the lab portion of the class will focus on fitting these models in R. So the software, I would imagine all of you have experience with at this point. If you haven't used R yet, let me know through email and we can go over that outside of class time. I would like to start, or I'm going to start the lab next Wednesday with the assumption that everyone's seen R before. If you've taken 378, which you have to be in the class anyways, you've used R to fit a linear model. And the work that we're going to be doing in this class is not a large leap forward from that. So there shouldn't be any issues in terms of getting set up. If you want to use RStudio, that's perfectly fine as well. It's the same functionality going, that will be, it's the same functions that we'll be using regardless. All right. Okay, so there's no required resources for this class, but the lecture notes that I am going to provide you have been built using a variety of different textbooks. So those textbooks are listed under other learning resources. And as we progress through this semester, I will make reference to the books that I am using and where the examples that I'm using are coming from and where the material that I'm using is coming from. So if you want to dig a little bit deeper into the topic, you'll have a particular reference to the sections that I have been using that you can refer to. And if you're interested in just having a book to reference on the side, these are the 4 main textbooks that I use to build the course. So you can look into acquiring copies of these. And if you need a particular passage or you're interested in a particular passage, let me know and I can try and help you get your hands on that. Okay, I mentioned before that this is going to be a pretty traditional course, at least in terms of how we're going to, at least in terms of assessment. And really in terms of structure and delivery, it's going to be what I consider to be a pretty traditional course as well. The assignments are worth 20% of the final mark. The term tests, in which there are 2, I'll show the dates for those momentarily, are worth 20% of the final mark. The project is worth 20% of the final mark. I'm going to show you, go over the project with you momentarily, but again, pretty traditional project, and it's effectively the same project that you had in Stat 378, except we're using a generalized linear model instead of a linear model. We have a lab exam. So according to the master course syllabus, there is a laboratory component to the course. So in the last lab, which is March 31, we'll have a test in R. The term examinations obviously will not use R. And then we'll have a final exam. So you can see that the distribution of the marks is pretty even. It's effectively 20% per component, with the final exams taking up 40%, but they kind of, they average out to 20 anyways. So it's pretty fairly distributed, or it's very evenly distributed throughout the semester. So everything kind of contributes the same to the final mark. Okay, we're going to do 4 assignments. The first assignment is due on the 21st of January. It's posted for you. I'm going to go over it with you momentarily. It's effectively a mini project, and it is essentially the same kind of mini project that we had in Stat 378. The only difference, and I'll talk more about this momentarily, is that I'll provide you the data set, so you don't have to spend time looking for the data. But your goal on the first assignment is basically just to fit a linear model and write a report on your analysis. But again, I'm going to talk about that in more detail momentarily. Okay, so we have 4 assignments. That means each assignment is 5% each, 20 over 4. The due dates for the assignment are given on page 3 of the course outline, and they're repeated on the last page of the course outline, which gives the tentative timetable for the class. 2 term tests, they're roughly a month apart. So our first term test is roughly a month from today. And then our second term test would be roughly a month after that. And then the lab exam is the last lab of the semester, which is March 30th, I believe here, but I thought it was the 31st. Just gonna make sure. No, March 30th, that's correct. Okay, and that'll be basically like the lab exam will be an R test. Okay, so you'll have some questions that you have to answer based off of using R to fit the models that we talked about throughout the semester. All right. And then we have the project, which is due April 5th. So that's the last day of class. The project includes an oral presentation. So the April 5th class will be a class devoted to presentations of the final projects. Okay, so each of you will be responsible for giving a 15 to 20 minute presentation. There's only 4 students in the class and we have an hour and 20 minutes for the lecture. So that gives us about 20 minutes each to give our presentations. And then you have to submit a written report as well. All right, so I want to discuss the first assignment so that everyone understands the expectation. And then I also want to discuss the project so that everyone understands the expectation. But it's kind of nice because the project is going to be very similar to the first assignment, except that you're free to explore more methods and you can choose the data yourself. All right, so the first assignment, which again is due January 21, is a written report where you discuss a model fitting process and evaluation of a linear regression model. So this is this is effectively a kind of like a smaller version of what you did for your Stat 378 project. And the reason that we're doing this is because the starting point for this class is a review of the model fitting process for the linear regression model and the structure of the linear regression model. As you will see, once we get into the second lecture set and move forward, the linear model is a special case of the generalized linear model. It's essentially the case where you assume that the error terms are normal and the response variable is a continuous variable across the entire real line. So the linear model is in fact a special case of the generalized linear model, and it serves as the basis sort of for where we're going to go with this course. So this assignment is really a review of material that you've already seen, but we're going to go over the key sort of strokes and we're going to go over the big picture items today and maybe on Tuesday if we don't finish lecture set 1 today, of what I mean by the model fitting process and how you can approach fitting a linear model in R. On Wednesday in lab, we will go over the actual process of fitting the model and deriving certain terms for that model. But again, all of this is review. So this is all material that you would have seen before and studied before. So the report itself does not need to be long, 6 to 8 pages, which doesn't include references, figures, and tables. The data set I will provide to you with the response variable. So what you are trying to accomplish in terms of what you're interested in discussing will be set up for you. So you don't need to find the data or determine the response variable for said data. I'm going to send an email after class and provide that to you. And in terms of your report, there is a overview of what your report should include on the assignment handout. And in addition to the assignment handout, there is a guideline and the marking rubric that shows you all the components that are expected within the report for assignment 1. In this class, a lot of the assignments will include open-ended questions like what you're seeing here on the first assignment. That's part of taking a 4th year course is, for lack of a better term, removing the training wheels and not providing guided questions the entire semester. There will be assignment questions and there will be assignments that are, let's say, more traditional and guided. So there will be questions on the second assignment that ask you to conduct or to work through proofs to show certain properties of the exponential family, for example. So you're going to get a variety of question types throughout the semester. But the really important part of this course is the ability to run your own analyses of data sets. This is what we're most interested in, or this is the skill set that we're most interested in building up. And what we're going to see throughout the semester are many different types of models that can be used in a variety of different situations. So there's a lot of flexibility in how you can approach the final project for this class, which as you can see from the description, is essentially the same as the first assignment, except that you now are able to use any of the tools that we talked about throughout the semester. And you're able to pick your own data set. We're going to talk about the structure of the data that you should be looking out for and the types of, well, we're going to talk about the structure of the data that you should be looking out for in a little bit once we start the first lecture set. But the beauty of this suite of generalized linear models is that you're really not limited in terms of the form the response variable has to take on. The purpose of this class really is to show you how we can still utilize linear models even when the response variable is not, say, a normal random variable or a continuous random variable that fits across the entire real line, right? So your choice of data set does not have to be, or can be, motivated by interest. So you should be able to use almost any type of multivariate data set for your project. And then it's just a matter of, fitting different types of generalized linear models or fitting one specific linear model depending on the questions that you're interested in asking. Okay. All right. Does anyone have any questions so far? Okay, I'm not seeing any. All right. In terms of submission of the assignments, we're going to use CrowdMark. So for the first assignment, this is really actually quite straightforward. There's going to be one box in CrowdMark that's like, upload your written report here. It's just easier for me to grade it in CrowdMark. It follows that your submission of the projects and the assignments will have to be PDF format. But if you're using Microsoft Word to type up your report, all you have to do is save as PDF or export as PDF, and you can upload it directly. If you're not sure how to do this, just let me know and I can send you a screenshot of the process that you would follow. But it's really as easy as just clicking Save As and then selecting PDF as the format type. Okay. And if you haven't used CrowdMark before, you can also let me know and I'll send you a video on how you can use it. Very straightforward though. It's basically just an online Dropbox where you just drop your PDF file and it'll sort the pages automatically. Okay, cool. So that's the first assignment. The write-up for the description that I showed you here and the guidelines, so the rubric and the explanation of the different components of the report are provided on the course website, which is on Blackboard. So you can review those, and that's due 2 weeks from tomorrow. And I will send you your data set and response variable right after class. And then the project write-up that's shown here and the description of said project is also shown, is also given in the course content folder of the course website, and you can start hunting for data as soon as you want. As I mentioned before, like really all you're looking for is a data set with more than, 4 or 5 variables in it so that you can at least perform some kind of variable selection process. And you're really not limited by the types of variables that are in the data set because of the flexibility of the suite of models that we are going to study. That being said, it's going to be a few weeks before we get into the different types of generalized linear models and their applications in R. But once we get there, I think the process of how to fit those is very straightforward. So you'll be able to start exploring those very quickly. Cool. All right. So turning our attention back to the course outline, the rest of the outline really just contains all the normal explanations or all the traditional explanations that you would see in other class outlines. So we use the same grading scheme across all of our lectures. or all the expectations are the same as they are across any lectures. Of course, unless there is an accommodation required, we ask that you don't record or redistribute any of the materials that are provided to you in the lecture. That being said, I'll be posting this lecture video for you after class, as we again are online until January 21st, at least until January 21st. All right, and then on the last page of the outline, we have a tentative schedule of topics for the class. Okay, so this week we're going to work through lecture set 1, which is a review of regression analysis. So this is going to be sort of my crude summary of stat 378 and the key components from stat 378. So we're not going to focus too much on the proof and the derivation of the linear model. We're going to focus on the model fitting process and the aspects of the model fitting process that you would want to include when you are using a linear regression model to try and analyze a data set. Next week, we'll get into the actual meat of the course, and we'll start with a theoretical explanation of the derivation of the generalized linear model. And this will include a discussion of the exponential family. And then in the following weeks, we'll talk about different types of generalized linear models, leading up to a discussion of survival analysis in weeks 9 and 10. And then depending on where we are in the course and if we're still on time and whatnot, we will also discuss some other related topics that could include, for example, an introduction to the Tweedy generalized linear model or a study of longitudinal data. And these will kind of be, in some sense, bonus material that you could see on the lab exam on March 30th. All right. Okay, so that's the plan. Hopefully we're able to stick to it, and hopefully it's interesting. Any questions at this point? Not seeing any. All right. All right, so our first lecture set, as I mentioned before, is going to be sort of a crude summary of stat 378. So I'm just going to kind of go over the main topics of the process of fitting a regression model in R. In our lab section next week, so our first lab session, which is on January 12th, January 12th, yeah. We'll actually look at how we would do this in R. So we'll go through some examples of sort of a basic model fitting process. On the first assignment, additional marks will be awarded for students that kind of go outside the expectation or outside the descriptions that are given in class. So, I really want to see some creativity and forward thinking on the ideas that are present, or on the general ideas that are presented in the lecture set and in the lab. Okay, so we're going to talk about the general definition of regression analysis. Then we're going to look at specifically the linear model in both of its forms. We're going to talk about the model fitting process very generally. Obviously, when you're using software to fit models, this is the model fitting process is done sort of behind the screen, if you will. So, via the LM function, we're going to fit a linear model using the least squares estimators, for example. And we're going to focus more on interpreting the model and analyzing the model. So following that, we'll talk about diagnostic measures and residual analysis. And then we will talk about methods for conducting inference, which can also be done using R output, and then a few other considerations that might arise in the fitting process. So for example, variable selection would be one other key component that you would be interested in, that you would usually be interested in exploring when you're using any kind of model, because the simpler the model, the easier it is to interpret. Okay, so what is regression analysis in the most general sense? Well, I like to think of it basically as a suite of tools that are used to link some response variable to some set of explanatory variables. Okay, so there's some variable that we're interested in studying the behavior of, conditional on another set of variables that would be present in the same data set. So typically, or actually in all situations, regression analysis is really only going to be appropriate when you have a bivariate data set or a data set that is multivariate. And what I mean by that is that you have observations that are emitting more than one measurement. So in the context of regression analysis, we're going to be working with multivariate data sets. And the sort of traditional clean description of what that data set is going to look like is given in the table on slide 3. So here we have, and it's kind of broken up for us, but if we include y with the x values, this is an illustration of a multivariate data set with p is equal to k plus 1 parameters. Okay. So what we are looking at here is a data set with p variables, but we have split the variables into a set of response and explanatory. So we have k explanatory variables and then the one response variable that we typically call y. And what we're trying to do is link the response variable y to the k predictors using some model. And I think most traditional or desirable outcome of this linkage is to try and predict where y is going based off of those explanatory variables. But what underlies that model fitting is assumption validation, residual validation, and variable selection. So while we might have k predictors that we can use, that doesn't necessarily mean that we want to use all k of them. Okay. But this description shown here, or this illustration, is the kind of data set that you're going to be looking for your project in this class. You'll see an example of it on the first assignment as well. All of those data sets are multivariate, and given the setup of the response variable, they're going to follow this structure by design. All right. So in regression analysis, we have, as described before, our response variable y, and then we have our set of k explanatory variables that we typically call x. We usually refer to the response variable, or we can also refer to the response variable as the dependent variable. So we're saying that y is conditional or dependent on the explanatory variables x. Those explanatory variables are often also called regressors or predictors. So there's a lot of different names that have the exact same meaning within the context of these experiments. But in general, what regression analysis is assuming is that y can be modeled as a function of f of x. So in the most general case, we have the regression model shown here on slide 4, where we have y equal to f of x, or f of x1 through xk, plus some epsilon, which is an error term that is basically associated with the model because we know we're not going to have a perfect fit of that function to the response variable. Okay. Any questions? Cool. All right, so I guess the simplest, or the second simplest type of model in terms of regression analysis would be the linear model. So in the linear model, we're basically saying let f of x be equal to beta 0 plus beta 1x up to beta k times xk plus that error term. Now, in traditional linear regression analysis, the beta 0 is known as the y-intercept. So this is going to be the value of y when all of the predictors are equal to 0. And I'm sure most of you are familiar with this. So this will be y hat when x1 through xk are equal to 0. Okay, beta 1 through beta k are what we call the slopes. In regression analysis, the slopes effectively represent the expected change in y for a 1 unit increase in x. When we have multiple explanatory variables, the slope terms are interpreted conditional on the other values. Okay, so this is expected change in y given a 1 unit increase in xk conditional on xj not equal to k. Okay, so basically a very clean interpretation, which is one of the really nice things about regression analysis is every time we fit this style of model, our interpretation of the slopes are going to be consistent. So we're basically just modeling the change in y given a 1 unit increase in x. And if we have multiple variables in the model, we're just going to condition on those other variables. So it's a very natural interpretation. And in almost all situations, it's very easy to understand what these values are telling us. Okay, now the other key component of the regression models or the linear regression models is that we assume a normally distributed error term. This assumption of a normally distributed error term, and then I should just be clear in case so this is normally distributed with mean 0 and variance sigma squared. Now, this attachment of the normally distributed errors, if it's true and we have evidence that these errors are normal, in terms of the model fitting process, this is very valuable to us because it essentially means that our process of fitting the model or finding the estimates of beta 0 through beta k is very easy. And if it is true that these error terms are normally distributed, it also means that when we do things like fit the model in R, we can actually we can use those returned estimates reliably. It is in some sense restrictive, as you will see throughout the course, and as you might have already started to realize through your studies in statistics, things in reality, you know, a lot of data is not normal, and things and variables that we might be interested in study don't follow bell curves that can be described by the normal distribution. You know, there might be a lot of things that follow bell curves, but that doesn't mean they're normal. They could be t-distributed, for example. And more generally, a lot of the time, the response variable that we might be interested in describing isn't going to be normal either, right? And we're going to see momentarily that the effect of this error term is effectively that the response variable itself is also going to be normal. All right, so that being said, when we're fitting linear regression models, these are the assumptions that we are making. or this is one of the key components of the assumption that we are making. It's worth pointing out that if we are in a bivariate situation, so a situation in which we have a single response variable y and one explanatory variable x, then we would be fitting what is called a simple linear regression model. So this is, in my opinion, the simplest, maybe not even in my opinion because it's in the name. So this would be the simplest regression model by terminology. Right, so we have y, the response, as a function of x1, which is our explanatory variable. Right. All of the terms in this model are the same as they were described in the more general case above. One of the nice things about this situation is the interpretation of beta 1 is very straightforward because you don't have to condition on anything else. So in this situation, beta 1 is telling us directly the expected change in y given x. The error term is still normal. And in terms of the model fitting process, this just makes derivation of beta 0 and beta 1 very straightforward. And I'll show you an example of what I mean momentarily. Right. Now, as we progress through the semester, we're typically going to be working with the multivariate version of the linear regression model. So that original model that we discussed on slide 5 is typically referred to as the multiple linear regression model. For the multiple linear regression model, it's actually easier to work in a matrix notation when describing the model and describing the properties of said model. So for the MLR model, we can also write bold face y is equal to bold x times bold beta plus bold epsilon, where epsilon here is now multivariate normal. Okay, so this is and the underscore here just means vector notation. Okay, and the dimension here is little n. Okay, so that means in this situation, we have a mean vector, so a vector of zeros, and then we have a covariance matrix, which has no correlation and sigma squared across the diagonal. So it's basically telling us the variance of each variable's residual term. All right. So given this notation, we can actually write down the properties of the model with a lot of ease. So for example, we can show that okay, so one thing we can do is write that okay, so let's say like we wanted to give the mean and the variance, for example, right? So find the mean and variance of y given a fixed value of x. Okay. Okay, well, this is pretty easy to do. So we can say, okay, the expected value of y, or sorry, these should all be underlined because they're bold-faced. The expected value of y given x is going to be equal to the expected value of x beta plus epsilon, which is going to be the expected value of x beta plus the expected value of epsilon, right? And then x in this situation is a constant. Beta in this situation is also a constant. And then our epsilon term is normally distributed with mean 0 and variance sigma squared over IN. So this is going to be simply 0 because the expected value of a constant is equal to 0 plus 0 because the expected value of epsilon is the mean of its distribution, which is 0. Right? Or sorry, the expected value of a constant is equal to the constant. That's a bad mistake, which is going to be x beta. Right? And actually, regardless of the normality assumption, we can work this out, but we would have to know the mean of the residual or the distribution and the mean of the residual term in order to get this result. We can do a similar thing with the variance, right? So for example, if we wanted to find the variance of y, okay, then we can say variance of x beta plus epsilon. Now in this case, we're going to have the variance of the constant plus the variance of a constant plus epsilon. So the constant does not affect variation. So you can shift the random variable any direction that you want, and that's not going to play any role on the variation of said random variable. So we're just going to have the variance of epsilon in this case. And that's going to be sigma squared times IN. Right. So the point being, again, that this matrix notation is really just allowing us to express some of the properties of the linear model very directly. And in this case, we can have direct representations of the expected value and the variance of our response variable conditioned on particular value of x. It's also easy to show that under this representation, we would expect that, or it's easy to show under this representation that the distribution of y conditional on x is also going to be normal, but it's going to be normal with a mean of x plus beta, right? So that follows directly from the statement given above here. Right. So we can say it follows that y is distributed normal x beta sigma squared. Okay, so given how does the SLR respond to another form of distribution like Poisson? Okay, so as we're going to see what, so the question, or no, everyone's here so they can read the question. As we progress through the semester, we're going to learn about how to handle situations where the response variable is of a different distribution. So for example, there's a generalized linear model that's designed to model count data. So when the response is effectively a count that occurs in a frequency that sort of follows a Poisson distribution. And we're going to talk about ways of evaluating that. It's not the same as direct residual analysis, but what you do is kind of study the property of the expected Poisson, compare it to the distribution of the response. But essentially, what you can do in the situation where you have, if you want to make like this SLR model and the distribution is like a Poisson, you would take a generalized linear model for count data, which we'll study, I think in like week 9 or so, or week 7, something like this. And you're just going to link it to that individual explanatory variable. Hopefully the relationship is strong. I mean, it's when you're doing these direct one-to-ones, it's not always a situation that you're going to get a good fit, but that would be one approach that you could take. Does that make sense? Okay. When you change the distribution of the response, so instead, in this situation, we're assuming that Y is not normal, but it's Poisson. You have to change the model formulation. And as a result, the process under which you find the estimate of beta 1 and beta 0 is going to be different from the process that you use for the SLR when the errors are normal. Does that make sense? Okay, and we're going to talk about that. So we will, you're kind of jumping ahead, but we are going to we will look at the situations where we have responses that are counts in more depth later in the class. And we will look at the model fitting process for that type of response in some detail. It's a tricky process, but we will study it. Another reason why normality is so valuable is it makes the model fitting process very straightforward. Once you start changing the distribution of the response and the associated error term, or changing the distribution of the response, really, like you'll see once we get into the form of the models, that it's not exactly the same as what we have here, but once you start changing the distribution of the response, the way that the model fitting process works actually changes with it. So it's almost like each one has kind of a unique process, and some are easier to understand than others. But normality is always the kind of the easiest one. Okay, so we've talked a little bit about these model assumptions, and we've talked a bit about the distribution of the error term that we attach to said linear regression model. So we can think of this error term, so the distribution of this error term and the expectation of how Y would be linked to X as a set of assumptions that we would need to evaluate when we're using a linear regression model. So we can write those assumptions out in a 4-step rule-based kind of approach. So for example, the first thing that we're going to assume when we fit a linear regression model to a data set is that the relationship between the response and the predictors is linear. Now, as we're going to see, as we progress through the semester, is that, or as we progress through the next week, really, is the evaluation of this first assumption actually falls pretty naturally out of the evaluation of the residuals. So you can model the linearity directly just by building scatter plots, for example, of the response versus the explanatory variables, and just effectively making a somewhat subjective decision about whether or not it seems like a straight line would fit that data appropriately. But if the residual relationship holds and the properties of the residuals hold, typically the regression or the linear relationship is going to hold as well because of the form of the model. The second assumption is something we're going to talk about in more detail today. So that is evaluating the error term assumption. So the error term, epsilon, is normally distributed with mean 0 and variance sigma squared. Okay. Also, in the case of the MLR models, the errors are uncorrelated. Now, With that being said, in practice, it's in the situation where we're fitting an MLR model, having perfectly uncorrelated errors is not going to happen when evaluating the covariances directly. But ideally, the correlation between the errors is going to be very small and as close to zero as possible. If we're in a situation where the error correlations are very high, then we can be in a situation of what we call multicollinearity. And in that particular situation, variable selection becomes extremely important because we do not want strongly correlated variables to appear in the model. In one sense, it's redundant because if they're strongly correlated, they're probably giving the same amount of information. And then in terms of assumption validation, it is violating the third assumption. So we are making the assumption that these error terms are uncorrelated. So that is that the off-diagonal elements of the covariance matrix for the error term are as close to zero as possible. And typically we employ guidelines. So, you know, like if the correlations are greater than some cutoff, which can be subjective, but let's say like, for example, the correlations are greater than 0.9, then that would indicate multicollinearity is present. And we need to deal with said multicollinearity, typically through variable selection and removing highly correlated variables from the model. Okay, and then the last assumption, which is kind of follows directly from the third assumption, is that the observations are uncorrelated. This is really the same thing as the error terms being uncorrelated, though, in terms of how we would deal with it. All right. So when we are fitting a linear regression model to a data set, we can think of the process of fitting said model as being run through 4 different steps. The first thing we just have to do is specify the model. Okay, so you're basically just declaring, and we'll talk about this in more detail, but you're basically just declaring the response and the explanatory variables and the model that you're interested in exploring. Now, when we're actually working through these processes on assignment 1, for example, or even on the project, most often you're going to start with the most general model, which would be the model that links the response to every single explanatory value. So the specification or proposal of the initial model is going to be my response variable is a function of everything that I have. And through assessment of the assumptions, we will make a determination as to whether or not that model specification is useful. And a lot of the time, what's going to happen is you're going to run into situations where particular variables are not useful given the other variables are in the model, most likely some multicollinearity between some of the variables, and the process of evaluating which variables you actually need is going to become more and more important. So this idea again of variable selection through methods like forward, backward, or stepwise regression is going to start from the main or the main model or the most general model for the data set that you are working with. Okay. And we'll look at some examples of how you can run these in lab, but we'll talk about them kind of loosely today. Right. The second step would be to estimate the parameters of the model. Obviously, we need to actually build an empirical model in order to evaluate it. Okay, the third step will be to evaluate the fit. So this is where the actual refinement of the model comes into play. And then conduct inference. So once we have, and step 4 is really conditional on the fact that after step 3, you have a model that obeys all the assumptions of the linear regression process. Because you could just go to step 4, but if you're using a model that violates the assumptions, then you can't reliably use the model for inference. So any of the conclusions that we might reach are not going to have any value to us. Okay, so we'll look at these steps in a little more detail now. Okay, so step one, which is the specification of the model. This basically just means propose. In the case of regression analysis, okay, so we're going to propose a model that links the response to the predictors, like for example, y is equal to beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 3 x1 x2, right? So this could be one of the possible models that you explore. Okay, so in step two, we're going to estimate the parameters of the model. Okay, so now this particular step is actually pretty straightforward if we're using software. So this is going to be most likely done through software like R, right? And then if we're going to use software, it's basically just going to be done through like the LM function or the GLM function, right? However, if we needed to do this by hand, then we can use techniques like maximum likelihood estimation, or the method of least squares, right? So these would be different ways that we could accomplish this goal. Okay. And then of course, maximum likelihood estimation is the approach that we're going to see throughout the semester. So this is typically how we fit the models that we're going to be studying in this course. Least squares, the method of least squares is something that you can utilize for the simple linear regression model, for example. In the case of the SLR model, it's actually pretty easy to show that the method of least squares and the MLE returns the same result, which is actually beneficial because, as you will know, or as you should recall, maximum likelihood estimators have a number of strong isentopic properties associated with them. For example, they are they're unbiased, they're consistent. So showing that the method of least squares is actually equivalent to these things means that those least squares estimates are also going to follow the same properties because they're the same estimators, right? But again, most likely we're going to look at the model fitting processes for the different models we study in some detail, but in terms of the project and evaluating generalized linear models and regression models, model fitting isn't done by hand, especially when you're working with large data sets. Like that would be basically impossible. So this is usually just done through, the LM function or the GLM function and R, this sort of thing. So our role as statisticians really comes into evaluating the model. So once we get to the third step. So on the third step, we're going to assess the fit. So we're going to assess fit through diagnostic analysis and residual analysis and this sort of thing through diagnostic measures and residual analysis. Now, in the case of the linear regression model, a lot of the diagnostic measures you will have seen before. So things like R squared, Cook's distance, the DF betas, DF fits. You know, there's a whole suite of different diagnostic measures that we can utilize to evaluate the fit of the regression model and to evaluate in the influence of particular observations on the regression model. Residual analysis is obviously, or I assume is a term that everyone has heard before. This is basically just this is the process of evaluating those model assumptions that we place on the error term. And this can be as simple as just studying the direct residual and the distribution of those direct empirical residuals. But there are other residuals that we can utilize as well to evaluate those same properties and to, again, kind of discuss or study the influence of particular observations on the regression model. But most often on step 3, what we're really trying to do first and foremost is use residual analysis to evaluate those model assumptions, particularly on the error terms. And then under the assumption that the model assumptions hold, that's when we would start to turn to diagnostic measures to evaluate the actual fit of the model. It might be the case that the residual term or the error term follow the distribution and have the properties that we expect them to have, but that doesn't necessarily mean the model is going to fit well. And that's where our diagnostic measures come into play. So things like R squared or the adjusted R squared, for example. Okay. So typically we would start by evaluating the model assumptions. Okay. And then evaluating model fit. Okay. Okay, and then in step 4 of the process, we're going to look at inference. So this is actually going to be the process of using the model to answer some meaningful questions about the population that we're going to study. Right? So use model to answer questions about the population of interest. Okay, and this can be done in a number of different ways. And the questions can vary depending on what it is that you're interested in studying. For example, if you're interested in looking at the relationship between the response and the predictors, this would serve, or inference about the model parameters would serve as a natural way of studying the influence of a predictor on a particular response variable. If you're interested in studying or in the predictive capability of the model, then we have, for example, prediction confidence intervals or conditional mean intervals that we can use to assess how reliable an estimate of Y is for a particular value of X. I mean, there is, just a whole suite of different things that you can use these models to accomplish. But most often, I would say that what we're interested in is studying the relationship between the predictors and the response variable and any interactions between those predictors and the response variable. Okay, so this can be accomplished through hypothesis tests about the model parameters and slash or confidence intervals for the predicted values. Yeah. That is all to say that when we're talking about inference and we're talking about model validation, it's not like there are consistent steps that you can follow. And obviously, once you're evaluating the model, for example, on step 3 of this 4-step process, residual analysis is going to be a key component of that because evaluating the model assumptions has to be done. But once you get to the inferential aspect of the model fitting process, this is where things can become very interesting. And the number of questions that you can potentially ask and try to answer when you have a model that fits well can be, very open-ended. And on the first assignment, for example, and even on the project, the direction that you take the inferential step is, up to you. You can look at relationships between the variables. You can look at evaluating the predicted values of the variables. I mean, there's no right or wrong way to approach this step. It really just depends on what you're interested in studying and what, for example, the particular project that you're working on is interest, or what the, what I was going to say is, like, if you're doing an analysis for a particular company, it just depends on what they would be interested in knowing given the data that is provided to you. Okay. So I was going to take you through an example of how the model fitting process for the SLR model would work. Again, this would just be a very general overview of how we would actually fit an SLR model if we had to do it by hand, for example. But again, this is something that's going to be done traditionally in R. But in the course, as I had mentioned before, we will look at maximum likelihood estimation for the different models that we're going to discuss so that we have an understanding of what it is that R is actually doing. But really, it's the model fitting step where our work as statisticians comes into play. So it's the evaluation of the model and understanding what it means for the model to be fitting well that we're most interested in. All right, so very briefly, like just as a refresher here, if we were to fit an SLR model and we wanted to understand the process that was taking place in the software we're using, there's 2 approaches that are traditionally used to fit an SLR model. So the process of maximum likelihood estimation and the method of least squares. The method of least squares is typically the approach that we teach at 1st and 2nd year levels. And it's discussed at the 3rd year level in addition to MLEs, or the maximum likelihood estimation approach. That being said, if we were to take the MLE approach, it starts from the fact that the epsilon term is normally distributed, right? So we have the error term here is normally distributed with mean 0, variance sigma squared. So that means that F of epsilon, so the density of epsilon, can be written as 1 over the square root of 2 pi sigma squared multiplied by the exponent, negative 1 over 2. I guess I'll follow the way I have it written here. So this is going to be epsilon squared over 2 sigma squared, right? So this is just the density of the normal distribution being applied to this particular value, epsilon. Okay, and then from this, it's easy to show that the likelihood of beta 0, beta 1, and sigma squared is going to be equal to the product from I equals 1 to n of 1 over the square root of 2 pi sigma squared multiplied by exp times yi minus beta 0 minus beta 1 xi squared over 2 sigma squared. Okay. And this gives the log likelihood of beta 0, beta 1, sigma squared, which is going to be negative n over 2 log 2 pi minus n over 2 log sigma squared minus 1 over 2 sigma squared times the sum from I equals 1 to n of yi minus beta 0 minus beta 1 xi squared. And then basically all we're doing from this point is just taking the derivative of the log likelihood with respect to each of the model parameters, setting it equal to 0 and solving for that term, right? So from the score functions for each model parameter, we have B0 tilde is equal to y bar minus B1 tilde x bar, comma, B1 tilde is equal to the sum from I equals 1 to n of yi xi minus x bar over the sum I equals 1 to n of xi minus x bar squared and sigma squared tilde is equal to um, 1 over n times the sum I equals 1 to n yi minus beta 0 minus beta 1 xi squared. So the point of this little refresher is just to give you some indication of what's going on behind the scenes, right? So when we're fitting these models in R, for example, or any other software, like these are the calculations that are actually taking place, behind the screen. So when you get that output from the model fitting process and you have your slope and your error term or your variance and your y-intercept presented to you, this is how they're actually finding it. And you can verify these values directly or even compute them yourselves. And it's good to understand the processes that are taking place behind the screen because it just gives you more information and allows you to better understand what it is that you are actually doing when you fit these models. Okay. But again, it's the next aspect of the model fitting process that's going to really be the important part of what we're going to work on throughout the semester. So that is that evaluation of model fit, which again, in the case of the linear model, a lot of the time just boils down to a residual analysis and then an assessment of the diagnostic measures and then variable selection and then rinse and repeat on the simplified model. Okay. For the generalized linear models that we're going to study later on for the majority of the class, we're going to learn about different measures that we can use to evaluate those fits. Again, most of the model fitting process is done through maximum likelihood estimation, but we will see that the processes that we can undertake to evaluate the models are going to be very similar to the processes that we see here in the case of normally distributed errors, right? So it all kind of builds on this foundational piece. Okay, so not unsurprisingly, I'm not going to finish lecture set 1 today, but it's okay. We'll finish it on Tuesday, and then we can look at the actual input in R on Wednesday. So it's kind of nice that we're not going to be too far ahead once we start lab on Wednesday. So on Tuesday, we will continue with lecture set number 1. And then on Wednesday, we'll have our first lab where we go over these processes in R. And then on Thursday, we will likely start lecture set 2, where we build the foundation for the generalized linear models that make up the key part of this course. Okay, so have a good weekend. I'll talk to you guys on Tuesday. I have office hours tomorrow if you have any questions, and I will send you your data set and response variable pretty much right away here. And I'll also send you a link to the my YouTube channel where I'll post the lectures that we have online throughout the semester. All right, so talk to you guys later. You too, man.